Okay, so yeah, my last personal conference on-site was 3 years ago in Austin, so I feel super excited to be here again on-site. So nice to meet every one of you here. My name is Han. I'm the senior machine learning engineer from Instacart ML infrastructure team. So I'm super glad to be here, sharing with you folks about our story on how we start our journey on Ray, how we find out the very first use case on Ray at Instacart, which is fulfillment machine learning. I will talk more about it later. And how we used to handle the fulfillment machine learning parallel training workflows in production, and how we find it limited, and how we improve it with the help of Ray. Okay, so this is the rundown of my today's talk. First, I will go very quickly on what is Instacart, how it works, why machine learning is super important at Instacart. And then I will give you the overview of the problem set of fulfillment machine learning at Instacart. And then I will go into some deep dive of the system architecture on how we used to support the parallel training jobs on Instacart fulfillment machine learning and how we improve it with the help of Ray. And in the last, I will talk about our integration work to integrate Ray with the existing Instacart ML ops. All right. So what is Instacart and how it works? I guess some of you here may have heard about us or even made some orders from Instacart application. Our value proposition at Instacart is actually very straightforward. We are running an online platform to deliver groceries and non-grocery items from the store you already love to your storefront as fast as 30 minutes. Behind the scene, there are actually a lot of complexities running this platform. We have the customer-facing application, which is a shopping app you will be using. Our searching and discovery infrastructure to help you find the items on the rack. Our logistic infrastructure to fulfill your order. And the application our shoppers are using when they are working at the store. We are running a four-sided marketplace. We connect customers to a personal shopper who deliver the service in real time. We partner with local retailers to give customers access to local stores they are familiar with. We offer coupons and other incentives from our brand partners who can increase the value proposition back to our customers. And machine learning is widely applied in almost every single edge of this graph, to name a few: search, item ranking, advertisement, and fulfillment marketplace, which is the use case I will talk more about later. We are now covering US all 50 states and Canada. As you can imagine, each market is unique and brings its own challenges. As a result, as a machine learning engineer working at Instacart, the approaches that we build have to consider all the differences and complexities. And here is the scale of machine learning problems we are solving at Instacart. We are partnering with 900 plus retailers across 75,000 plus stores in 13,000 plus cities in US and Canada. We are enabling 5,500 plus brand partners to connect their products with potential customers. We are helping our customers to find the items they love out of an item catalog as big as over 1 billion products, which is almost 3 times of US population. And at its core, Instacart runs a real-time logistic platform. Our fulfillment machine learning engineers are working dedicatedly to connect millions of customers with 600,000 plus shoppers to get every order delivered efficiently. We operate a very dynamic and complex fulfillment marketplace. Machine learning plays critical roles throughout the entire life cycle of every order. Here are some examples of fulfillment machine learning models. We optimize routing of deliveries in real time. At any moment, given a set of deliveries and stores of a region, how do we decide which store to use for a particular delivery? For multiple deliveries in the air, which deliveries should be grouped as one batch to be fulfilled by one shopper, and at the same time without delaying any orders from any customers? Predicting and balancing supply and demand is extremely important in real-time marketplace. If supply exceeds demand in the market, we lose money and reduce shopper happiness because shoppers are sitting idle without any profit. If instead, the order demands exceed available shoppers in the market, we lose customers due to limited availability. We predict ordered ETA to simplify the checkout process with more clarity. We personalize ETA on every customer visit. Instead of customer selecting out of static delivery time windows, we predict ETA on a continuous time frame with better control on conversion, cost and margin, etc. For all the mentioned and unmentioned fulfillment scenarios, our machine learning engineers apply different types of algorithms and continue to evolve the model with the most up-to-date machine learning techniques. I will not cover about details in modeling today. But in the end, most of those models end up with the same patterns of training. For a given type of model, we want to create a huge batch of training jobs parallelized on one or multiple horizons. The most common horizon is geographical locations. We call it zones. For example, San Francisco South Bay Area is a unique zone. Some models running on real-time supply and demand would have another horizon, we call it day hours, which is the store open hours throughout the day. This means that one unique model type will fan out to thousands of parallel training jobs in production training. At Instacart, we have over 2,000 unique zones in our product, and for each zone, we have at least 8 hours of store open hours, counting up to more than 16,000 zone day hour horizons. We have over 30 types of models running in such highly parallel pattern, and the number of models keep growing as our machine learning engineers are producing new models. We want to target to retrain each model with most up-to-date input data on a regular basis. This brings us a challenge on how to execute those highly parallel training workflows in a scalable and efficient approach. Next, I will show you how we used to support highly parallel training jobs in production, why we found the previous solution not scalable, and how we improved the system by introducing Ray. Here's the architecture overview of legacy solutions running on AWS ECS. There are two parts of the service running together as publisher-subscriber system. On the left-hand side, we launch a cron-like scheduling service with Redis clock backend to push training tasks on each model on a regular basis, for example, daily or weekly. Each model has one training task per zone or per zone day hour, which is ranging from about 1,000 to plus 10,000 of tasks. When model application is scheduled, the full list of parallel training tasks is pushed to one of those task queue running on Redis message broker. Each task queue is subscribed by an executor service running a group of Celery distributed workers on the right-hand side. And each worker gets allocated with one task to execute each time, process it, and update the task results in message backend. In order to make deployment process easier for our machine learning engineers, which is the author of the model, but at the same time don't want to spend much time handling system complexities, in production, it's quite common implementation that multiple models produced by the same business unit share the same task queue to ease the complexity of job execution. When machine learning engineers want to enable a new type of model, they don't need to make any changes in Redis cluster or in Celery worker services. What they need to do is to redeploy the cron scheduler service by adding training task definitions and identify the name of task queue to get those applications connected with. Well, this solution used to work pretty well at the very beginning when we have very few models. However, later as we onboard more and more models in our production, we found this implementation is not scalable and has a bunch of limitations. First of all, we make multiple models share the same task queue and same set of distributed workers. Later, it turned out to be very difficult to tune the resource requirement that fits all models. Therefore, we had to be very generously in provision computer resources and at the same time be very conservative in configuring the number of concurrent Celery workers per host. This ends up with each host provisioned with many CPU and resources, however, running in very low very low utilization. And the end-to-end completion time to finish parallel training job of multiple thousands of zones takes very long because we have very limited number of parallel workers. Since every Celery executor service is shared by multiple models, we couldn't easily increase the number of concurrent workers per host for a particular model just to speed it up. So it typically takes 1 to 2 days or even more to retrain a model with very high number of parallel tasks. We are running this system as a long-running service, but in reality, our model just needs to be retrained every week or every couple of days. Therefore, our task queue may sit idle most of the week. We need to tune the auto-scaling policy very carefully, otherwise we are wasting computation resources and company money. We are running this monolithic service hosting many models, making it very inflexible to manage dependencies. For example, we couldn't change the Python package of one model without impacting other models. And this system is too complex to automate. It's hard for machine learning engineers to run any local test on their laptop or on the notebook platform without diving deep into the system architecture, unless they go through additional steps to bring everything up by themselves, such as local Redis server and separate sessions to start Celery workers and application tasks. And it's high maintenance to manage service for all model types. Any change on one model requires a redeployment process that potentially affects all other models. And even worse is that if we make changes on the executor side, for example, we want to move one model from one queue to the other, it introduces an even more complicated deployment process because we need to redeploy both scheduler and executor services. Here are some graphs exported from our monitoring dashboard. Just want to give you some ideas on how a low utilization scenario looks like. In fulfillment area, most machine learnings are practicing with algorithms such as regression, classification, etc. Such algorithms are usually very lightweight in terms of resource usage. For example, in the left-hand side, we are running a model on a 16-inch CPU instance. However, the CPU utilization is only around 10 to 15%. You may ask in this case, why not provision with a smaller instance? Well, as mentioned, there are multiple models sharing the same queue. Some models are lightweight and some are heavier. We had to provision big enough machines to leave enough headrooms to suit all models. This is the major drawback of hosting models as a monolithic service. Another pain point is we set up a long-running service, waiting for the scheduled retrain job to kick in. This may end up with a very unbalanced load on time series. On the right-hand side, I give you an example of a very unbalanced task queue. This queue is not running any task over 60% time of the day. Therefore, we need to tune the auto-scaling policies with extra efforts, expecting the service to downscale when the size of Redis queue is small as such. However, it's also pretty common that we see another side of the extreme, where there are many models produced by the same business unit queuing up in the same task queue, such as what this graph is showing you. The number of tasks in queue ranges from 300 to over 1,000 all day round. In such case, we either have to manually move some models to a lighter loaded queue by going through the service redeployment, or we do horizontal upscaling by adding more Celery workers to the queue to process the tasks. However, keep in mind that for the added workers, they will be still processing very lightweight algorithms. Therefore, the horizontal scaling will end up with adding more and more low-utilized workers and continuously increasing our bill. And we also found the implementation of scheduler service often comes with a very hard-coded cron job definition. Here's how it typically looks like in the form of pseudocode. This requires the model owners, the author of every single code block here, to manage and balance the load of each queue all by themselves. For example, if there are too many tasks to be scheduled on the same day, same time window, and on the same task queue, we either suffer from higher latency to complete tasks, or we compromise by further scaling the number of workers horizontally. After reviewing the existing solution, to better understand the pain points and the limitations, we learned that we need to build a new parallel execution architecture, which is expected to be more resource efficient, more flexible in setup, faster in end-to-end execution, easier to automate, and with the support of isolated workflow environment. We redesigned and proposed a new fulfillment training platform to leverage the parallel execution API of Ray and Ray cluster. Here's a system diagram of Ray-based solution. At the beginning of each training lifecycle, we deploy a Ray cluster consisting of one head and multiple distributed worker pods on AWS ECS. The resource specification of Ray cluster pod is completely customizable based on model requirements. Once the Ray cluster is online, we create a client pod with connection established to the head node of Ray cluster, and then submit the master workflow to the head node through Ray job submission API. Once the master workflow starts running on head, it fetches the full list of zone IDs to be executed, and then fan out one remote function per zone ID through Ray Remote API. Since in our workflow pattern, all training tasks are parallel to each other, there are no dependencies between tasks. Master workflow running on the head node is the owner of all tasks. This makes the scheduling process behind the scene very straightforward. The master workflow requests resources from distributed scheduler to execute the task. Once worker resources are available, the scheduler grants the request and responds with the address of the worker that is now leased to the owner. The master workflow schedules the task by sending the task specification with zone ID over gRPC to the leased worker. After receiving requests of the task, the worker spins up the training workflow by taking input data from data storage based on input zone ID. The return value of each training workflow is also very small in size, so that the worker returns a value in line directly to the master after training completes. There are many changes between the previous solution and the current one. One of the most significant changes is that we now move out of long-running service to a serverless architecture by leveraging Ray. This brings us a lot of advantage compared with the legacy solution. We no longer put multiple models sharing the same distributed executor service. We now bring up one Ray cluster dedicated to connect with one model application. We no longer host long-running services. We bring up a Ray cluster at the beginning of the life cycle and bring it down once all workflows are complete, which gives us the advantage of save more resources. And we have more complexities to customize each Ray cluster to better accommodate the specific settings per model. For example, we are able to install different versions of Python packages per model workload. We are able to be more specific and accurate in resource requirement per worker. We also find it very simple to adopt Ray in existing model workflow implementation. Here's some pseudocode from the existing workflow implemented by our machine learning engineer. We only need to literally add one line of code to change this into a Ray executable class object or task function. And in addition to it, we only need very few lines of code of a for loop to orchestrate such remote calls asynchronously with rate limitation handling if necessary. Here's a diagram to quickly illustrate the idea of workspace isolation between different models. As you can see, even though we are developing both models with the same set of machine learning libraries, such as scikit-learn, we are still able to provide flexibilities to the owner of each model to develop with different package versions by creating separate Ray cluster associated with each model. Here's an example of better CPU utilization on the same type of node instance. Here we have 16 CPU machines running the same model training jobs. In our previous system, we are unable to create concurrent Celery workers per host due to the limitation that multiple models share the same task queue. There was only one Celery worker running on each instance with CPU utilization as low as 10 to 15%. Our new solution built by Ray, we could be more accurate in per worker resource requirement. Based on our training benchmarking, it's sufficient to allocate 2 CPU per training task. Therefore, in the Ray cluster setup, we create each worker with 2 CPUs. This allows us to create multiple Ray workers running concurrently on each instance, and as a result, greatly increase the CPU utilization. Here is some early testing result of running a real-time supply-demand gap forecasting model. In the test, we are handling 1,500 unique training tasks over 715 zones. We provisioned 10 M6A 4X instances as distributed executors. In the previous implementation, we are limited to create only 1 Celery worker per instance, which gives us only 10 concurrent workers to execute parallel tasks. In the Ray-based solution, we are able to be much better utilize, we are able to much better utilize the compute resources. We end up with creating 60 Ray workers to execute parallel tasks out of the same set of instances. As a result, we are now able to greatly speed up the training completion time from previously around 4 hours to now like 20 minutes. We also heard from our machine learning engineers, the owner of this particular model, that they plan to further parallelize this model by applying 8 hourly zones, like 8 hourly horizons per zone. This will give us around 12,000 parallel tasks in production, which will take the previous system about 1 day to finish, while on Ray, we expect to complete all tasks within 2 to 3 hours. And next, I will talk about our integration to integrate Ray with our existing ML ops. 2 months ago, our team announced Griffin, the Instacart ML Platform, which is a hybrid of third-party solutions to support diverse use cases, and in-house abstraction layer to provide unified access to all types of solutions. Griffin helps our machine learning engineer quickly iterate on machine learning models, effortlessly manage product releases, and closely track their production application. Griffin consists of 4 major components here: an interface to use this platform, an orchestrator to schedule pipelines, a data platform to manage features, and a computation platform to run the training and inference jobs. Let's take a closer look at the workflow orchestration layer in Griffin. Here we have a workflow manager to schedule and manage machine learning pipelines. It leverages Airflow to schedule containers on a regular basis and utilize an in-house abstraction, we call it ML Launcher, to containerize task execution. ML Launcher integrates different compute backends. One of the most common ones being used by our machine learning engineers is AWS SageMaker, but we also support different types of backends. As I've mentioned in previous chapter, we are now converting the parallel training tasks from a long-running service to a serverless application. This makes the automation much easier by integrating Ray applications with Griffin workflow orchestration layer. Here we rely on the workflow manager to run on Airflow to retrain the model regularly. And we extend ML Launcher to support backend where Ray cluster and Ray client are running on. Here's the integration diagram of ML Launcher plus Ray. What ML Launcher requires the user to provide is quite high-level parameters, including containerized workflow image, runtime to launch Ray cluster, resource and dependency requirement of the Ray cluster. ML Launcher then takes turns to create customer resources of Ray cluster, confirm all workers are in running status, and then create a client pod with Ray cluster connection parameters, and then launch the training workflow wrapped by the Ray submit command. In this way, we minimize the onboarding efforts and overhead from machine learning engineer side. What they need to provide to Griffin is simply high-level parameters, leaving our ML op tools to handle the complexity of workflow and workflow automations. And on the controller side, we rely on kubeRay to deploy Ray operator as a controller of provisioning, updating, deleting Ray cluster resources. So as a next step, we plan to roll out more parallel training workloads on Ray cluster. And at the same time, we also look into various use cases of Ray at Instacart. For example, distributed training models to train large-scale dataset, ML libs to enhance the next-generation modeling, we are super excited about our future vision of ML Infra plus Ray at Instacart. And I'm looking forward to learning more from everyone here about your insights of applying Ray to scalable production machine learning. So if you are interested in the offline discussion, please feel free to reach out. Thank you. Do we have Q&A session? No.
Yeah, like 4 minutes.
If anyone has questions, I can answer it. Otherwise, we can leave it offline discussion.
Hi. So in the beginning, you mentioned that you had a 12-core machine, and then you were not really utilizing it completely because some jobs took 2 cores and some had 12 cores. But in the middle, you also mentioned that in the Ray actors that you created, each actor had just 2 cores.
Yeah.
So did you have actors which had higher cores as well, or
Yeah,
can you have
because
that?
there are different levels we can control the resource requirement of distributed task running on Ray. So we can configuring our Ray workers with a specific resource requirement on the exact number of CPUs and memories to like of each worker container, or like we can handle it in the programmatic way, like when we create the Ray actors or the Ray task function, we also have those parameters to specify the exact like compute resources we want to execute this actor or this task function. So there are 2 levels. So one is on the programming level. If the owner of the code understand the resource utilization really well about their functions, they can insert it into code. Otherwise, they can leave it as a high-level parameters for the machine learning ML ops tool to handle it when create those distributed workers.
So you can create a list of like zone ID resource requirements and then send it to Ray, and Ray will take care of it.
Yeah. Any other questions?
Hi. Hi, how much of Ray is actually exposed to your users? So like, do users interact with the Ray API, or like, are they able to dive deeper into the Ray API, or is it mostly higher level, like, hey, like you have the ability to map over zones and that's kind of it?
We have different type of users. Like some users, like they are looking for some like abstraction libraries to convert their task into Ray executable like immediately. In this case, we provide our own like Python library abstractions to help our users to convert their actors or functions into Ray executable. But we also support different users like which understand better of Ray and wants to really fine-tune their workflows. For example, the distributed training use cases that user needs to write a lot of code of Ray train, Ray dataset. They understand better on the system like the Ray is operating on. Then in this case, we also leave the flexibilities for those users to write their own code. But in the end, we provide those launching like tools so that no matter you are like you are the user relying on the high-level abstractions, or you write all your code, like all those container workflows can be launched through the unified toolings.
How are you handling concept drift monitoring and other observability factors for 1500 models?
We are integrating our metrics of monitoring like with Datadog. Like we can push the metrics we care about like through Datadog and create the customized dashboard based on the product lines. And if like you are talking about like another level of like model quality monitoring, we also like working closely with Rise on those type of monitoring and validation. So different type of monitoring.
Yeah, we're at the end of time, so any remaining questions can be taken offline.
Okay, thank you so much for being here. Thank you.